We'll now provide a recursive procedure to get a LUP decomposition of an arbitrary matrix A of size m by n, where n is greater or equal to m, and for convenience of recursion, as we usually do, we'll assume that m is a power of 2. If the number of rows in A is not a power of 2, we can always augment this matrix with a block of identity matrix and then perform an LUP decomposition of the resulting matrix. So we'll also assume that matrix A has rank m. Then our procedure will be able to construct matrices L, U, and P such that matrix L is lower triangular and invertible, so that all the elements on the main diagonal of L are non-zero. The matrix U is upper triangular, so here we have zeros, but our procedure will make it so that this square submatrix of matrix U is a matrix of full rank. So all the elements on this main diagonal are non-zero as well. And P is a permutation matrix. The fact that our procedure keeps the invariant that this square submatrix of U is invertible is quite important for us, and we'll use this fact in the recursion. The sizes of these matrices are, of course, m by m, m by n, and n by n. And we start with the recursion base for m equal to 1. Now it means that our matrix A is just a single row, and if the rank of this matrix is equal to m, then this row contains a non-zero element E somewhere. If the first element of this row is 0, we can permute the columns so that E is exchanged with this 0 element, and from this we get a permutation. And if now we have a matrix where E stands here on the first element, then this matrix can be decomposed into a lower triangular and upper triangular matrix, where the lower triangular matrix is trivial and the upper triangular matrix is our original matrix A itself. So the base case is kind of trivial, but we see that even in this base case, we might need a permutation matrix if the first element of our matrix row is 0. And now we'll proceed with the general case of m greater than 1. In case when m is greater than 1, we can split our matrix A into two matrices, B and C. Each of these matrices will have size m over 2 by n. And the first computation that we do is computation of LUP decomposition of B. So we now take B as a product of three matrices, L1, U1, and P1, and this can be done because if A is a matrix of a full rank, then B is also a matrix of a full rank, and so we can perform this decomposition. So the block B can be decomposed into the lower triangular matrix L1 multiplied by an upper triangular matrix U1 and multiplied by a permutation matrix P1. But what about our block C? We can actually see that if we take an identity matrix here and 0 blocks here, and if we take yet another block here and make it equal to C P1 minus 1, then this thing is a decomposition of our matrix A. Because when these guys are multiplied by the columns of this matrix and then multiplied by the permutation here, we get exactly the LUP decomposition of B, so we get the block B. And when these guys are multiplied by the columns of this matrix and then by P1, we have exactly the block C. So this is why we put P1 inverse here. Let's denote this matrix C times P1 inverse by D. D is C times P1 inverse. And so now we can rewrite this as D. How close are we to LUP decomposition of A? This matrix is actually already lower triangular, because identity block here is a lower triangular and L1 is lower triangular. Now if we look at the triangle in the second matrix, in a decent LUP decomposition, it should be filled with zeros. And well, part of it is already 0 because U1 is an upper triangular matrix, so we have zeros in here. But we still do not have zeros here. And let's denote this square block of matrix U1 by E, and this square block of D by F. And let's provide a different decomposition for this matrix, a decomposition of this sort. The first matrix would still have blocks L1, identity, and 0 block, but instead of the other 0 block, we'll have FE inverse here. The second matrix would have the upper block still equal to U1, but the lower block will be D minus FE inverse U1. And we note that the matrix E indeed has an inverse, because that's our assumption. Our assumption is that LUP decomposition for a matrix of full rank will return a triple of matrices such that the left square block of U is an invertible matrix. And the third matrix in our decomposition is still P1. So what do we have now? As soon as we multiply these rows by these columns, we get FE inverse U1 minus identity FE inverse U1 plus identity D, which is just D. And this is exactly what we would get if we multiplied these guys by these columns. So this portion is kept intact. But let's look on the same square subblock of this matrix. If we consider the matrix E inverse U1, then as the leftmost columns of U1 are exactly the matrix E, then this matrix actually has its leftmost square submatrix as identity block. And thus this product has its leftmost square block as F exactly. And so the difference between these guys have the leftmost block as zeros. So this is actually a null zero block. So now let's denote this guy by G, and we put G to be equal to D minus F E inverse U1, so that we are able to put G in here. And we know that we have more zeros already. We have zeros here, we have zeros here. So now we need to put zeros in this triangle and we are done. And to do this, let's look just at these non-zero columns of matrix G, and we call this block of G as G prime. We note that G prime have rank m over 2, and thus we can perform an LUP decomposition for G prime. So we can find matrices L2, U2, and P2 that make a LUP decomposition of G prime. So now if G prime is decomposed into L2, U2, and P2, how do we plug these things in this scheme? Well, what we can do is we can plug this guy in here, where we had an identity block, U2 goes here, and P2 goes in here. And it can be checked that the resulting scheme still resolves to matrix A. So instead of identity block, we have now L2. Instead of G and G prime, we have now U2. And P1 will now have to give place to P2. But P2 needs to permute only the columns in this portion, but not the zero columns that we had here. So we augment it with a block of identity matrix. And as this matrix had n columns, here we have order n minus m over 2. Here we have order m over 2. And we have zeros here. So these matrices, permutation matrices, can be actually stored and processed combinatorially. Not as matrices really, but as permutations that we need to make. So this is just a permutation of some of the columns, and this is a permutation of possibly all the columns. So now finally we see that U2 is an upper triangular matrix, so that we have zeros in all the lower triangle of our second matrix of decomposition. And the product of these guys is a permutation matrix. So now we denote this guy by U and this guy by L, and this would be the output of our program. And now let's do a bit of accounting. What is our complexity? So it can be checked that multiplying permutation matrices, if we treat them combinatorially, can be done in linear time if we store the permutations properly. Computing inverse matrices for permutation matrices can be also done in linear time. And let's keep track of the rest. The time that we've spent for LUP decomposition of M over N matrix is bounded by first producing LUP decomposition of B. And B is an M over 2 by N matrix. Then we permute the columns of C, which can be done in quadratic time. We need here also to compute inverse of E, which can be done in time big O of M to the power of omega plus little o of 1, because E is a square upper triangular matrix. Then F times E also takes this time, because both of these matrices are square matrices of order M over 2, and computing the product of this square matrix by this rectangular matrix can be done, as we have checked, in time big O of N times M to the power of omega minus 1 plus little o of 1. So this is the time needed for multiplication of a square matrix of order M by rectangular matrix of order M by N. And now we see that this guy is dominated by this guy anyway, so we keep just one of them. And finally, we need to compute an LUP decomposition of matrix G prime, which is dominated by this term. So we can just put 2 before it. And now note that our second parameter n here in the recursion is fixed. So only the first parameter is being halved. And so for fixed n, and for m not exceeding n, we see that our complexity TLUP as a function of a single parameter does not exceed twice the complexity for halved parameter plus this guy. And this is what usually gives us m log m complexity, which is dominated by this term anyway. So this complexity can be bounded by big O of n times m to the power of omega minus 1. And finally, the complexity for running the procedure on a square matrix where m is equal to n is thus big O of this guy, which is again our big O of n to the power of omega plus little o of 1. So we finally have proved that our recursive procedure, with all the necessary computations, with genuine matrices and with permutation matrices, leads to the time which is roughly the same as multiplication of two matrices, and this determined by the matrix multiplication exponent. And this scheme of computing LUP decomposition recursively works in the arbitrary field, which allows us then, as we know, to compute inverse matrices over arbitrary fields and solve systems of linear equations and compute determinants as fast as just multiplying two matrices by the asymptotics of time complexity.